Okay, so one more video for class was 6. Um, it's very, very similar to the homework assignment. It's just to give you some familiarity with this. I'd say homework. I guess problem sets. That's what they call it. Yeah. It's just to try to give you some familiarity, if you weren't already, with some statistics and going through this process. So we got 10 samples of axial force placed on a support have been recorded in the table below. Also included are 10 yield strength values gathered from a batch of 836 steel. By the way, 836 is a very generic steel. It's a specification that the steel will have a minimum yield strength of 36,000 KSI. Or 36 KSI, excuse me, not 36,000, but 36 KSI. It is known that both load and material are consistent with a normal distribution. We want to find the probability that a strength is less than 35 KSI, the design factor and required diameter to achieve 80% reliability, the design factor and required diameter for a rod for 99% reliability, the safety factor and associated reliability if a preferred size from table A17 is specified that complies with part B, right? Answer reliability in 4 significant figures. And I wrote that you should use Excel for stuff because why would you otherwise? So here's the values, the force and the strength. So we get the average and the standard deviation from them. With that, we can get a Z transformation of the what are we dealing with here? Of the strengths, right? So we use the Z transformation of the strengths. So we find where does 35 KSI lead? Well, we end up finding it's a 20. For that Z with a Z transform of 0.7678 gets her an R out off of the thing of 22.2213, or there's a 22.13% chance that it's going to be less than 35 KSI. Now we do the coefficient of variance transformation, and we did 80%, and we find that, or either interpolating or get it from Excel, that it has a transform of 0.8416. And we're able to push those things together with this equation and find we need to have a design factor of 1.059. Now I've broken my standard rule of only 2 decimal places for a safety factor, but only because this is an in-between number that we're going to use to calculate something. So that's appropriate. So if we do that and we go back to the equation we previously used for an axial case right here, this isn't like a universal equation. It only applies when you're dealing with axial problems. We get a diameter of 1.284. So if I was going to pick a diameter for that, I'd either have 1.30 or 1 3/8, which is 1.375, right? Because 1 1/4 wouldn't be big enough. Okay. So then let's do the next one, part C. Let's go 99% reliability. And so we get a Z transformation right there, or a transformation for a Z, I should say. Apologies. We're going to go backwards for 99% reliability. Here's the Z that we would get. We get a design factor 1.178, and we run through that. And actually, we're probably doing okay for here. And I'm not quite sure why I didn't choose 1 3/8 again. I think I would have if I had to do it again. 1.3 isn't good enough, but the 1 3/8 might be. So anyway, then we go to the last one here. So we skipped back to B, and I chose the 1.4, probably because it matched for both of them. But I guess I'm not exactly following my own instructions. But we get the stress of 28.6 KSI. And then we can work backwards, and we can find the safety factor, or that does the analysis, say, well, how safe are we? And then we could also work backwards again from that and now find, well, what's the reliability going to be in this new case? The fact that we rounded up to a size when doing the preferred size method, we increased the reliability significantly. So that's the idea there. And there's the Excel where I've put these into place. Nice thing to have to use this Excel, because now I can use it over and over again when you have to want to change a problem up. So anyway, that's the last video for class 6. And maybe somebody actually watched this. I don't know. Maybe. We can hope. Goodbye.